So let us write the mathematical models for various signals and systems, maybe a few case studies. You can understand there are n number of signals and systems just for basics to understand what is real time, what is the mathematically representing a signal, how they behave when you use different data types, and so on. So to begin with, let's see square wave. So this square wave has two states. One is high state, other is low state. Between high state and low state, let's have a 50% on time and 50% off time because it's a square wave, 50% duty cycle. That means a delay of 10 milliseconds on, and for 10 milliseconds it is off. So 10 plus 10, total the duration of the signal is 20 milliseconds. So 1 upon 20 milliseconds is your frequency, that is 50 hertz. Let's display this waveform on computer monitor by using serial port. So serial print high state, serial print low state with a delay. So in this program, this function square wave generation is a function, and we have called from the loop, void loop, which is executed infinite number of times. So the program is getting compiled and is transferred from the PC to the CPU, where the device we have selected is ESP-32, Do It ESP-32 development kit, and the port is connected at COM3, which is shown in the device manager. The baud rate for this program is chosen 9600 bits per second. So once the program start executing, it will transfer the data with this 9600 bits per second. On time and 10 milliseconds off time. That means instead of square wave, you will be generating some rectangular waveform, because on time high state is 100 milliseconds, low state is 10 milliseconds. So you have made the change of the waveform, the nature of the waveform changed because between high state and low state, the the state time you have changed. That's the difference. Okay, so this is one way of generating a square wave. The second waveform is sawtooth waveform. Tooth waveform, the variable initial is 0 and from I is equal to 0, I plus plus for 100 count, I value we want to print. So a sawtooth is always a increment by 1 till the maximum count reaches. After that again I will become 0. So though mathematically if you see it's an incrementing the number, but if you see as a signal, actually it is a ramp type of a waveform. Let's see the waveform. So the program is loaded. If you see the numbers, it's always increment by 1 every time. But if you see this as a signal, see the plotter, as you can see, it's a sawtooth waveform where between one sample to the other sample, there is a delay of 100 milliseconds. If you reduce the delay, then the frequency of the sawtooth waveform will be increased. Alright, so this is the mathematical expression for a signal sawtooth waveform, which is nothing but a incrementing the number from 0 to some value. That's the peak. And after that again it should fall back to 0. The next signal is triangular waveform. In triangular waveform, it's incrementing to a peak max and decrementing from max value both. So it's a climbing as well as decrementing. So in this program you can see we have defined the wave, and that wave we have two loops, one for incrementing the count, other is for decrementing the count. Let's see the waveform. Program is loaded. If you see the shape of the waveform, it's incrementing from minus to plus and decrementing plus plus to minus. So both the peaks are there, positive and negative. And the frequency of the signal, that depends on the delay which you have used in the program. That will decide the delay. Delay will decide the frequency. All right. This is a triangular waveform, a mathematical representation. Then let's see the sine waveform. So a sine waveform consists of a fundamental frequency. So we are supposed to vary the angle and as well as the amplitude. So there is a inbuilt sine function is there. Let's pass the frequency term as well as the amplitude. Let's compile and download the program. So the program is loaded. Let's see the waveform. As you can see, the frequency term as well as the amplitude with a fundamental frequency in single frequency. Alright, so this is the sine function. So this is what exactly we are saying, that first try to understand what is a mathematical model of the signals and then systems which will process the signal. and what is the correlation of the input and output based on the system. Once you experience this, then you can go ahead with the interfacing of various sensors, actuators, and so on. This program let's generate two frequencies. One is, let's say, fundamental frequency. Second is with a multiple of the fundamental, let's say two times, three times of the fundamental, right? That's the, let's say multiple is you are defined three times. That means if you generated 50 hertz of fundamental signal, then the next signal will be generated is 150 hertz frequency. So W1 is fundamental signal, W2 is your three times of the fundamental signal of the sine function, and display fundamental signal. That the addition of fundamental plus third harmonic, then how that waveform looks like. You have generated one pure sine wave, second another pure sine wave which is multiple of the fundamental, we call as a third harmonic because three times this frequency, and addition of, if this third frequency is added to the fundamental frequency, how the waveform looks like, what is the shape of the signal, that we need to understand when we talk about the signals. What is the role of the frequency components in shaping the nature of the waveform? Let's see that. Let's compile and download. Program is loaded. If you plot the waveform, what you can see is there are three frequency components in this. Two signals indicate the fundamental and the third order frequency, and the third signal is looks like M shape, which is because once you add this fundamental with the third order harmonic, the shape of the waveform is no more sine wave. So that means, say for example, if you have a square wave, if you have a sawtooth waveform, a triangular waveform, or any other like ECG, EMG, EEG, all sorts of waveforms, and if they are non-sinusoidal signals, that means they have some other frequency components in it. So our duty is to find out that to shape the waveform, what are the frequency components are contributing, or the other way around. Whenever you come across any signal, what is the spectrum of the signal? Which components, which frequency components have contributed greatly to shape that particular waveform? That is called signal processing. Maybe eventually we'll discuss, we'll have a session on it. Alright, so this is called harmonic signal. So far whatever the waveforms we have seen, there is a mathematical expression exists, like sine waveform, triangular waveform, square waveform, and so on. Let's see a waveform where there is no straightforward single equation exist to shape the waveform. Let's say ECG waveform you want to generate, or EMG and other types of earth related signals, or atmospheric, space, any signals. If you cannot represent them by one single equation, then how do you generate such kind of waveforms? Since there is no straightforward equation exist, you have to use different techniques, maybe array technique like lookup table, or sections of the waveform. You can have multiple equations and then join them together and so on. So it's like a, If you have a non-linear system, how do you represent them mathematically? Because there is no one equation for that. Let's see. ECG waveform. Alright, so the program is loaded. If you plot the waveform, let's see what is the 9600 baud rate. So if you plot the waveform, as you can see, the waveform is, though it is a periodic in nature, but the output of the waveform, the nature of the waveform, cannot be represented by one single equation. So the PQRST of each is a signal. You have to write it mathematically by multiple shapes. Every shape has a different set of equation. That's how you have to model it. Alright, so far what we have seen is that how to represent a signal with the help of a mathematical expression. Unless you understand the signals, their mathematical model, there is no point in going for sensors. Sensor means what? It will give some a real signal, but that is converted into number. So you don't see them as a numbers, you see them as a signals. That's the reason why this session is important. Okay, let's see one example of, there are, though I have multiple examples, but one more example of what do you mean by a system. Because see, a signal is given, right? Like we have seen square wave, sawtooth waveform, triangular waveform, ECG waveform, like that. But how to process the signal? You want to, for example, convert that signal into frequency domain. Means how many frequency components are present in the incoming signal. Or you want to filter the signal, you want to amplify the signal, you want to attenuate the signal. That is called system. So signals and systems. So this program will convert your time domain signal into frequency domain signal. Right? It will extract how many frequency components are there in the incoming signal. Right? So how to implement a fast Fourier transform. So FFT is to convert your time domain signal to frequency domain and will give you which frequency component is contributing by how much value, so that that shape of the signal is made. So any signal, if you see, then if you convert into frequency domains, plot the spectrum, then you will come to know which frequency component has contributed to by how much amplitude, so that this shape is made. Alright, so program is loaded. Now if you plot the results, I think this time the bird rate is not 9600, it is 1,15,200. Now if you see the spectrum of a signal, it is saying maybe one frequency is a dominating its amplitude, other frequency slightly dominating, almost negligible. So this is called converting time domain signal into frequency domain by using Fourier transformation. So we will discuss about the transformation mathematical expression later on, but you need to understand how to convert these signals from one form to other form mathematically. All right. So that's all about this session. What are the signals and systems, and then how to represent them mathematically in a controller, and what do you mean by real-time sampling, real-time processing, and real-time communicating. All right. Thank you.